Problem 2. The tallest building in the world is the Burj Khalifa in Dubai. It stands 830 meters tall. So you get in the lift and travel to the top, and the lift accelerates upwards at 3 meters per second for the first half of the journey, and then it decelerates at the same rate for the second half of the journey. So let's draw a diagram. Here's the building. It's 830 meters tall. So halfway up is 415 meters. So you have an acceleration of 3.0 meters per second for this part, and then an acceleration of minus 3.0 meters per second for this part. So this is an acceleration downwards because you're slowing down. And part A says, what is the maximum speed of the lift during the journey? So to work this out, the maximum speed actually needs to be here, because up to this point we are accelerating, getting faster and faster, but after this point we start to decelerate, and so we'll be getting slower and slower. So the fastest will be is at 415 meters. So we need to find speed at 415 meters. So we'll need to go back to the kinematic equations in order to do this. And we know that we start from rest. When we get into the lift isn't moving. So the initial velocity is equal to 0. And so we can use the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the distance, which in this case is the height. Okay, so we've got v naught squared, that's 0 squared, plus 2. Now the acceleration is 3.0, and the distance which we cover is half the height, so 415 meters. And so this gives us that v squared is equal to 2,490, and so taking the square root of this, we get that the velocity halfway up is 49.9 meters per second. And then part B. So we should give this answer to two significant figures. So this is 50 meters per second to two significant figures. Now part B says, how long does it take the lift to get to the top of the tower? Now this is going to be absolutely symmetric because we're speeding up and slowing down at the same rate. Let's work out how long it takes us to get to this halfway point. So to this halfway point we can use the kinematic equation v is equal to v naught plus at. So v, we know that when we're halfway up our speed is 49.9 meters per second. The initial speed down here was 0 meters per second. The acceleration is 3, and the time, that's what we're trying to find. So t is equal to 49.9 on 3. And solving that, we get 16.6 seconds, which is equal to 17 seconds to two significant figures. But that's the time to halfway. Now at halfway we're travelling at 49.9 meters per second upwards, but at the top when we get out of the lift we've stopped, so we're at 0 again, but we have this acceleration here. So to work out the time we can use v, the final velocity is 0, is equal to 49.9 minus 3t, and this turns out to be the same as this. T is equal to 49.9 on 3, and so this is equal to 16.6 seconds, and so the t total is just equal to 2 times 16.6 seconds, which is equal to 33 seconds to two significant figures. So you can see that that's symmetrical. The time to get to halfway up was the same as the time to get from halfway up to the top of the building. Now part C says, what is the maximum normal reaction force felt by a passenger with a mass of 90 kilograms in the lift. Okay, so let's try and do that in this space here. Here's the passenger standing in the lift. Now, in this first half, the resultant force is equal to ma upwards. The forces acting on the passenger, we've got the weight force downwards and the normal force upwards. So we've got that because of Newton's second law, ma upwards is equal to the normal force upwards plus mg, which is going downwards. And so the normal force upwards is equal to ma upwards minus mg, which is going downwards, and so this is equal to 90 times, now this is upwards and it is 3, and then we've got minus 9.8 downwards, so that's plus 9.8. Now in the second half, this lift is going to be slowing down, so instead of being a plus 3, this would be a negative 3, and the reaction force would be smaller. So the maximum reaction force is going to be in the first half when the lift is accelerating. So that makes sense. When you're standing in a lift, when it starts to accelerate up, you feel a lot heavier, and that's because of the reaction force. So let's calculate what this is now. When we put this in the calculator, we get 1,152 newtons, and then we should just give this to two significant figures, so that's 1,200 newtons.